This is a discussion between me and my friend Carlos, who I met a few years ago at a series of Jordan Peterson lectures in Miami. Carlos works in insurance and recently has become interested in computer programming. We had a conversation a couple of weeks ago about Python and decided to jump on another call and record our discussion. We cover some philosophy of Python and computer science, as well as the differences between programming languages, things like compiled versus interpreted languages, high-level versus low-level languages, and then finally, toward the end of the video, we do a little bit of coding in Python. I hope you enjoy the discussion. I've done a lot of research about Python. I've learned a lot about it, and it's possible for me to just turn on my camera and talk to the camera, but it's way easier for me to access my knowledge and deliver it in a meaningful way when I'm having a conversation with another person. And the fact that you're interested in computer programming and you also have the context of studying Dr. Peterson is exciting to me. So I've been looking forward to this conversation. I'll give us a starting place. And if you have any questions along the way, ask me. If there's anything in particular that you want to talk about, then we can go there. It's not necessary for us to follow a particular plan, but I thought we might start by rehashing some of the ideas we talked about on our earlier call, beginning with what Python is. When I teach Python, I want to orient my students in the big picture, meaning before we get into the technical details, I want to help people to understand what is this thing that we're doing? Because Python programming works, like computer programming more generally, it works, and computers have changed the world. It's a different place than it used to be before computers were around. And that's interesting. The magnitude of change that has occurred as a consequence of computers and programming languages tells us something about the reality that we live in. And I am teaching Python for money, but ultimately I want to help people to orient in reality. So if I can do that while teaching Python, I want to. And I think one consequence of giving students orientation within the big picture in this way is that learning Python will be more meaningful. And because it will be more meaningful, it will be more memorable. And because it will be more memorable, they'll be better able to apply it. And so it seems like the right place to start. So I'm curious to know how you would answer the question, what is Python?
Honestly, I don't know. I know that Python is a program that can be used for multiple purposes.
That's right.
It's what I was briefly reading about was that it's easier than some of the other programs in computer programming.
Yeah, that's also true.
And that, as you were saying, it's sort of like a good navigation tool that can help organizations or companies improve their efficiency and just, I guess, automate workflows or automate tasks. And that's basically what I know, honestly.
Well, that's a good place to start. It's true that Python is simpler than other languages, and I can show you an example of that, actually. I'm going to show you how to calculate 2 plus 2 equals 4 in 3 different languages. Tell me when you can see this.
I can see that. Java, Python, and C?
Yeah. So if you're going to learn a computer programming language, Python's not a bad place to start.
So Java is the most wordy one, or would you say that's the most complex one for writing it?
Looks similar to C, but both more complex than Python. And there's some trade-off, and we can talk about that later. But yeah, so you're right. Python is simpler than C or Java. And you mentioned that Python can be used for different things. That's true. And it's not true of all programming languages. But I think maybe as a next step, we can say simply, Python is one kind of programming language. It has distinct characteristics from others, which make it useful for certain purposes. For example, since it's simple, if you haven't programmed before, it's a good one to learn first. But then if you want to understand that, we would then need to ask, what is a computer programming language?
I was about to ask you that. Yeah, I was about to ask you that.
So we're going to dig into that. But before we do, what would be your best answer today?
I guess it would just be the structure. I don't know what's behind the language, but I guess the language, it's the structure that represents something behind it that's making the programmer use that to achieve what he wants. So it's sort of like a mediating symbol of a piece of what the programmer wants to do.
Yeah. So that's actually the best answer I've ever heard. That's a great answer. You're right. So let's come back to that because I want to ask one more question. And that is, what is a computer?
It's clearly a machine tool that, well, I guess it's like an amalgamation of a bunch of different languages or potential you could use. Like, it presents you with like a bank of possibilities, and then you use those different languages to store information, learn information, something like that.
Yeah, that's amazing. This is great. You and I are on the same page.
Awesome.
Yeah, this is cool. I haven't been able to I have one friend who I can talk to about this stuff and he gets it. But yeah, this is going to be fun. So let's talk about what a computer is first, and then we'll come back to what a computer programming language is. Tell me when you can see this.
I can see that.
This is the stepped reckoner, which was invented by a guy named Gottfried Wilhelm.
Wilhelm. Yeah.
Yeah, so Gottfried Leibniz. He invented this in, I think, 1672, and it's a mechanical calculator. It could be used to perform basic arithmetic, addition, subtraction, multiplication, division, and it would do it using gears. So the key component is this device, and you see it's a cylinder with these bars protruding from the side, and each of the bars has a different length. And then just next to this cylinder is a gear that's positioned so that the bars strike the gear and cause it to turn. But because the bars are different lengths, you can shift the position of the gear so that differently sized bars strike it a different number of times. And so you can use this to count. By changing the position of the gear upward and downward, you can count to a different number. Does that make sense?
Sort of, yeah.
So like if I wanted to count to, I don't know how many bars there are. Let's see. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 bars. If I wanted to count all of these bars, I would shift this gear to the right all the way, and then the bars would strike it 9 times. But as it's positioned right now, only 1, 2, 3 of the bars strike it. So this gear is in a position relative to the cylinder that causes it to count to the number 3. And so with a sequence of devices like this, Leibniz made a device that you can use to calculate things. And that's interesting in itself because that shows us that we can mechanically represent logical operations. You can perform a logical operation in your head, like you can count to 3, 1, 2, 3, add another 3 to get 6, 4, 5, 6, but we can take that process and we can embody it physically in a device like this. So Leibniz did that. Then later, 1820, a guy named Charles Babbage produced this thing called he designed this thing called a difference engine, which is another mechanical calculator. It's got these complex array of gears. And this device calculates polynomial functions. So for example, if a scientist is trying to calculate tables of logarithmic functions for their work, he could use this machine to do it automatically to save him time. So we could say that a computer is a logical operation processing machine. Leibniz's stepped reckoner is an example. Babbage's difference engine is an example. And the body of the machine is designed to represent logical operations. Or maybe you could say an array of potential logical operations. The stepped reckoner can be configured to represent 3 plus 7 or 132 divided by 16, which is amazing if you've never seen a mechanical calculator before. But for us, we see that it's highly limited. So Leibniz produced a device with a certain amount of configuration potential. It can be configured to represent a set of logical operations. Babbage's difference engine could be configured to represent different polynomial functions. It had greater reconfiguration potential than the stepped reckoner, but still not nearly as much as a modern computer.
Right. 2 different curves.
What do you mean by curves?
Getting closer to the asymptote.
Oh, I see. Okay, right. Yeah.
It could be sense enhancers, like our vision's limited, our hearing's limited, our thoughtful abilities are limited. Obviously smell wouldn't, or touch or taste wouldn't get into that, but it's more about efficiency and scanning the environment right in front of you.
That's an interesting idea. Maybe another way of phrasing that would be to say that these machines are information transformers for the purpose of enhancing our senses. They transform information in order to enhance our senses, because I don't have an intuition for the most important academic papers written on machine learning for the last 100 years. Like I don't have a sense of that. And I know I'm not using sense like 5 senses. I'm adding intuition. But I go to the computer and it scans the environment and it gives me an answer. My other friend that I talk to about these things, his name's Jeff, and he runs a AI startup, but he's also a physicist. And he says computers allow us to see things that we couldn't see otherwise. So in data, for example, there are patterns which I cannot perceive with my eyes. You could give me a book of thousands of rows of data, and I could flip through that and I could read it, and maybe I could gain some useful insight from it, but it's too much for me to digest. I can analyze that data using machine learning algorithms, or even simple statistics and get a sense for its shape and its patterns. And so in that way, it's almost an extension of my eyes. It allows me to see, but I have a different thought. And maybe this is a overly cynical answer, but it's true, at least in some places. You could say the aim of maybe a certain kind of computer science is to create a god and subordinate it to yourself.
Yeah, I can see that. I can see what you mean by that. Do you think there's an alternative view of maybe when you define it, it's less cynical because it implies what computer science should do in one's life? Because I guess the other definition implies that you would want computer science involved in every area of your life.
Well, it almost is.
I know. Yeah.
And that's interesting because that means that the thing that computer science does is deep and generally applicable. It's a logical operation processing machine. And the reality that we live in is logical. We learned logical operations from reality. At the beginning of civilization, human beings were not astute mathematicians. We discovered math, and we discovered math because math describes the way the world actually works. Like, logical operations are real. We look at instances of things happening in the world, and then we abstract these mathematical principles. But then we can embody those mathematical principles. We can insert our abstractions back into the physical world in the form of a stepped reckoner.
Right.
And it works.
Like the tangibilization of concepts.
Right. It's the embodiment of an abstraction.
Yeah.
And it's because it works. Like that machine can physically process logical operations. And then I can use the answer, the output of that process to do something in the world, and I'll do the right thing. Like if I'm calculating a price, if I'm a cashier and you're ordering 5 different coffees for people in your office, I can add up the prices and the machine will tell me the right amount of money to charge you.
Right.
And that's based on our abstractions, which are based on our observation of instances of things happening in the world, and it works.
And there's just like an extra point, but I always find it interesting that there's so many people involved in that small transaction. Like the person who made the machine, the people maybe who made the machine, who thought about the ideas, who then the company, whoever sells those machines, person who takes care of that machine, person who wants coffee, the person who's giving them coffee. And it's just one moment in time, but it carries with it so much more than a small transaction. But that's just like interesting.
Mm-hmm. You could put the history of mathematics and the history of computation behind that also.
Yeah.
My point in saying that is computers solve a deep problem, which is processing logical operations. Because reality is logical, a logical operation processing machine can be useful almost anywhere. Maybe actually anywhere.
Are you saying like computers are maps and guides at the same time? Like they develop the maps out of very complicated and large amounts of data?
Computers can provide maps and guides, but they're better understood as machines. I think that's the best way to think about it. A computer is a machine. It's a certain kind of machine. It's a machine designed to process logical operations. And with a machine that's highly reconfigurable, you can represent almost any logical operation or complex series of logical operations that you can imagine. And because the world is logical, that means that you can represent almost anything. You can create a computer game that contains a whole world and characters and events and imitations of the laws of physics. And a person can enter into that world and live in that virtual world. It's a curve. It's not the asymptote. It's a map. It's not the territory. It's a representation, not the thing itself. And so it's not quite as rich as the world is.
Yeah.
But it's amazing how the level of detail in which we can represent the world in something like a video game is mind-boggling. Well, so now maybe we can return to the question, what's a computer programming language? A computer is a logical operation processing machine. We're no longer working with the step reckoner. We're no longer working with Babbage's difference engine. Now we have modern computers. And one of the fundamental components of a modern computer is a logic gate. And a logic gate, like an OR gate, is a kind of logic gate. And it might have 2 inputs, A and B. And this OR gate is an electronic circuit that monitors whether A is on or whether B is on or whether both are on. And if A or B or both are on, then this circuit sends out a positive signal, like it turns on. Okay. But if both of these are off, this circuit sends nothing. So then what I know is if this circuit is on, either A or B or both are on. I can use that kind of logic gate to represent something like, is it cold outside? A. Or is it raining? B. If it's cold outside or it's raining, then Carlos is going to wear a jacket. But if it's not cold outside and it's not raining, then Carlos is not going to wear a jacket. The modern computer has hundreds of millions of logic gates.
I see how that's what you're saying about those are logical gates. I guess gates it's because they can open or close. Like it's some of the millions that are inside a computer, some might be on and some might be off. I think I get it. Starting to get it.
With millions of these things, you can represent almost any logical operation you can imagine. And it can be as complex as millions of logical operations in a simulation of the world in a computer game.
And I guess could A and B, like there could be like the basic ones, I guess, and then there's like higher ones where it's like this A and means that all of these are turned on, these previous logic gates, and this B means that. So there's like a hierarchy to it.
Okay, exactly. Okay. Right. And so by connecting these logic gates together, you can represent a sequence of logical operations that's more complex. The problem is that unlike Leibniz's stepped reckoner, I cannot configure these logic gates with my hands. They're too small for me to see. They're too small for me to manipulate. And even if I could see them and manipulate them, I don't have time to reconfigure 450 million logic gates in a computer so that I can execute one calculation in my Excel worksheet and then reconfigure like 200 million of them so that I can make some adjustment. So I need an interface. I need to put a machine on top of this machine that allows me to interact with it.
That's the language.
Right.
Is it? Okay.
Right. Which you got from the beginning. It's an intermediary. That's just right.
So the other ones would be like the hard drive, or I guess there's got to be a physical side to all that.
The hardware?
The hardware. Okay, the hardware.
Yeah, right. Yeah. Okay, so a computer has a body. That body is a machine that is designed to provide potential for processing logical operations. Massive potential. Low-level programming languages help a user to convert that potential into useful work. But you and I don't interact with low-level computer programming languages. There are multiple layers, even, of programming languages. I don't want to stray into territory where I don't know what I'm talking about. Here's what I understand. A programming language like C is a lower level programming language than Python. That's why it's more complex.
So would Python have C within its structure?
It does, actually.
Okay.
Python is built using C. C is a lower level programming language that provides its user with more freedom to reconfigure the computer's hardware than a higher level language like Python.
Right. It's like cars, mechanic, and automatic cars. I don't know, those are the words in English. But like
manual. Yeah, automatic and manual.
Manual. Yeah, manual. So
right.
Something like that. Okay.
That's a nice metaphor because the manual gives you more control, but the trade-off is that it's more complex. At the beginning of this call, we looked at C and Java and Python, and you could see C and Java are more complex. Python is simpler. That's because C and Java give you more freedom to reconfigure the hardware of the computer. Python gives you less freedom, but what you gain is simplicity.
So like I was going to ask then, the most experienced people in computer science want to learn or probably already know about these other languages to the core, and they want to work. Like if there's an issue, they want to achieve something and they're in Python, they're like, this is not enough. They go down a layer. No.
That's exactly right.
Oh, okay.
So Python is what's called an extensible programming language. It is itself built in C. You would say that it's implemented in C. So the machinery behind, well, let's say this first. You can think of Python as an implementation and an interface. Like the programming language itself, you can think of as an implementation and an interface. The interface is what a developer interacts with, like a user, a programmer. But there's something behind the functions and the symbols that make them work with your hardware. That's its implementation. Python can be implemented in many different ways. I can have this interface that I want to provide to a user, a programmer, and I can implement it in C. I can implement it in, there are different, I won't get into it, but there are actually different implementations of Python. But the official implementation, the traditional one, the most widely used implementation is C. If I'm a experienced developer and I'm coding in Python and it does not provide me with some functionality that I need, I can write a new Python package in C or in some other language. I can implement it however I want, I think. I actually don't know what the limitations are on implementation of packages, but I know I could at least
go down a layer and there's more range than when you were in, that's the whole.
And then I can publish this package publicly. I can upload it to a repository where other people can download my package and use it in their code so that they don't have to rebuild this thing that I built. And this is one of the reasons why Python is popular. It is an extensible programming language, which means people who are experienced, who have the skill, are producing packages to solve problems all the time. And so almost any problem that you're going to encounter, especially as a new user of Python, somebody has already solved. So for example, Python has built-in functions and a standard library of functions. It provides a certain amount of functionality by default. It does not provide machine learning algorithms, but very smart people who code in Python and in C and probably other languages design machine learning algorithms that we can use to analyze data, and then they publish packages, upload them to these repositories. So when I'm coding in Python, I can import those packages into my code and use their work to analyze my data.
I was thinking also, like, would you think this is a good metaphor to understand it? It's like a body of research papers, like when academics publish things and other people cite it or other people use it to find other information. Would these be called patches or no?
So
function,
a patch,
I guess,
as I understand it, is an update to a piece of software, right?
Okay.
Like some developers published some software and there's a problem with it. And so maybe there's a security issue. And so they release a patch and that alters their program. Maybe it changes its functionality for the user. Maybe it doesn't change the functionality for the user, but it makes it more secure.
Right. Okay. So these are more like enhancements that you can add.
Well, yeah, extensions. Python is
right.
It's extensible. It's an extensible programming language. So when you create a package, you are extending the programming language. And language is a funny word for this thing. It's a machine. You're not talking to the computer. The computer is not saying, "Okay, boss, good idea." You're catalyzing a series of physical changes, electric changes, like electricity is moving through the circuits of this thing. And when I hit enter and I execute my code, I'm catalyzing this movement of electrons that results in an output. So the computer doesn't understand, but the creator of the language, like the developer of Python, has made this machine to function in a certain way. And this machine has parts. The creator of Python labels those parts with names. Like if I want to create a function that adds things together, I might name it sum. So this part of the machine called Python, which is labeled with the name sum, is going to do the thing that I call summing. So the creator of the language is speaking to you, the user, the developer, with the label that's placed on that part of the machine. And then if you and I are collaborating together on a project, then the labels of the parts that you use to construct your program communicate with me, your partner, so that I can look at your work and improve it and so on. So the communication in a programming language is happening between the developer of the language and the user, the programmer, and the people with whom that programmer is collaborating. But there is no communication between any human being and the hardware of the computer. You're just catalyzing a sequence of physical changes, but the design of the machine is such that that sequence of physical changes produces a useful output.
Embodies an operation, right?
Right. Accurately, precisely, correctly. Yeah.
So the layers would be like the electrical changes, and then the like C would be here, and then Python would be here. I
think machine code would be underneath. Like the lower levels, I'm still learning about the lower levels. I don't know if you want to know about this, so I'll make it quick. But as I understand it, the way that Python works is you write Python code, and then that Python code, that's called source code, is compiled into something called bytecode. I don't understand much about bytecode, but it's sort of like a lower level programming language. But this bytecode is not executed by your hardware. The bytecode is given to a virtual machine. I don't understand completely why Python is designed the way that it is, but the virtual machine in Python, in the Python interpreter, like the virtual machine, I think it's true to say the virtual machine is a part of the Python interpreter. And the Python, I got it wrong. Okay.
I thought it was in each computer.
No. Right. Okay. So now we've got that sorted out.
Yeah.
I think it's true to say that the virtual machine is a part of the interpreter. I could definitely say the virtual machine is a part of the Python machine, the Python programming language.
Right. Now I see. Okay. Interpreter. So, and I was thinking translator, like, okay. It's for Python to work in different operating systems.
Right.
It's like the front, whatever is having a conversation with a computer. That's what it...
Yep.
The bridge, sort of.
Right. And the virtual machine, I'm still learning about some of this lower level stuff, and I don't want to go into territory that I don't understand yet. But Python is an interpreted language. It is a computer programming language of a certain kind, which is called an interpreted language. That is contrasted with a compiled language. C is a compiled language. What that means is that after you write your C source code, in order to execute it, you must first compile it. Compiling translates your source code into machine code.
Source code is...
That's what you write.
Okay, and machine code is what's going on electrically?
That's the zeros and ones.
That's the zeros and ones. And that's what indicates, that's what doesn't make the electrical changes, but it's sitting there so that when you hit enter, or like when you create something in Python, it starts in Python, it moves down to this, this, and then the electrical thing goes inside your computer. Terrible way to put it, but I think you get what I'm saying.
I think I do. So right now, well, in order for your computer to do anything, eventually machine code needs to go to your processor. And I hope I'm getting this right when I say this. We're in territory that I'm still learning about.
Okay.
But a computer has a central processing unit, a CPU. And I think it's correct to say that that is the primary component. Machine code, I hope that this is true. I think that this is right. Machine code goes to your CPU, and then your CPU directs the remaining hardware of the computer to execute the instructions conveyed by that machine code.
Okay.
Machine code is binary. C is a compiled language, which means you're not writing ones and zeros. You're writing C, which is relatively human readable. And then your source code is compiled by a compiler that translates your source code into machine code that is sent to the CPU and then executed by the computer. There's an advantage to compiled languages because they're compiled. The work has already been done. I mean, your program is compiled, so you can feed it right to your CPU. One of the advantages of an interpreted language like Python is that your source code is executed. How do I say this? I don't have to compile my code. I don't understand exactly how this works technically yet. It has to do with the virtual machine. It has to do with the Python interpreter. I'm still learning exactly how. But what I can do when I code in Python is I can type in 2 + 2, and then I can just execute that, and I get 4. What's happening there is technically my source code is being compiled into bytecode, which is, I don't know, apparently it makes the language more efficient. I don't understand exactly how. And then that bytecode is sent to the virtual machine, and then the virtual machine produces machine code that's given to the CPU. I don't know, honestly. I'm still learning.
But there's a lot going on with just typing 2 + 2 and getting 4.
There are many, that source code goes through many sequences of transformation before it is executed by the hardware.
Okay.
Yeah, it goes through a series of transformations.
Going to ask, how do you start programming something with Python? Is it like just like a page where you know the language and you know what this means and you start writing as if you were writing like an essay or a paragraph, but obviously not using regular words, but using the specifics of Python?
I could show you a couple ways. Okay, can you see this?
Yep.
Okay, I am going to open the Python launcher. Can you see this?
Yes, sir.
Can you read the text?
I can.
All right, so this is the Python launcher. You can download this from python.org for free. This Python launcher is an interface that allows you to write and execute Python code. The package of software that you download from python.org includes this launcher in addition to the whole programming language. And you could think of the whole programming language, well, the creators of Python will often refer to the language as the Python interpreter. They'll often use those terms interchangeably, even though that's not completely precise.
Interchangeably, Python and Python interpretive?
Right.
Okay.
And the reason for that is I could open up a Word document like this and I could type Python code. I just typed Python source code in Microsoft Word, but I can't execute it.
Right.
In order to execute it, I need the interpreter. Well, and everything packaged with that. But the interpreter contains all of the rules of translation. Without the interpreter, this is just print, open parentheses, 2 + 2, close parentheses. The interpreter contains the rules that recognize this name, print, as a function. And it recognizes that this opening parenthesis indicates that what follows is an argument that
Mhm.
should be passed to this function. And then the closing parenthesis means that I'm finished with the arguments of the function. So the interpreter contains the rules of interpretation. So I can't execute in Microsoft Word, but if I go to the Python launcher and I type the same thing, or you know what I could do? I think I could even copy and paste this. I can copy the source code that I just typed in Microsoft Word, and I think I can paste it, into my Python launcher. And now, you see, it gives me the answer.
So you could write drafts in Word.
I could, yeah.
And then just...
So like, let's say, how old are you?
23.
Okay, so let's say Word is not the best place to do this because it automatically corrects my typing and I don't want it to. Carlos's age is 23 and Zach's age is 31. And now we want to calculate our combined age. Like, how many years together have we been on this earth? I could say combined age is equal to Carlos age plus Zach age. And then I can print that value, display it. Now I'm going to copy all of this. I'm going to paste it into the Python launcher. Oh, I mistyped it. I put an equal sign.
Yeah.
So I'll change that. And now what I can do is I just need to I don't have to type this in Microsoft Word. It's actually not the best way to do it.
Okay.
I could say combined age is equal to Carlos age plus Zach age. So now what I'm doing is I'm redefining this thing which I've named combined age. I had defined it as combined age equals Carlos age equals Zach age. Now I'm changing that.
You don't have to delete the other one? Or I guess You could go both ways?
I don't have to. I just have to redefine it. Now I can say print combined age, and it'll give me the right answer. PyFi has been around since 2018, so we're in our 6th year of operation. But this YouTube channel is brand new, and we just started posting videos. We're trying to develop our following so that we can earn business by sharing information with people on YouTube. And it would help us out if you would like the video, only if you really liked it. If you'd subscribe, if you want to see more of what we're doing, and if you'd share this with other people who you think might be interested. Thanks for your help.